Well, hello everyone. Welcome to the next seminar in series for the AnalytiXIN Manufacturing Data Assets project. Today's seminar is being held by University of Notre Dame and presented by Professor Jane Cleland-Huang and her team. So I'll let them take over and present their work.
Okay, so thanks everybody for coming to this talk today. So we're actually going to give our talk about something that's a little bit, that's very closely related to AnalytiXIN data, but is based on some other data sets in a whole different domain. And then Nafi's going to make the connections back to the early work that he's done on some of the AnalytiXIN data. So our other project, the main area of research for my research group, is basically in the area of UAVs. And Nafi, could you go to the next slide, please? So our work is funded by NASA, and we have a grant that looks at the safe deployment of small unmanned aerial systems through onboard monitoring and assessment. So you can see that there's a lot of kind of commonality between this and the data analysis that's going on with AnalytiXIN. And the video that Nafi just showed is just to give a little bit of a background. So we're working on this project where we have multiple UAVs. They all have onboard autonomous pilots. They have autonomy capabilities. They work together and they work in partnerships with humans as well as basically team members. So that's what we've been doing. Next slide, please. So for our NASA project, our goal is to develop, evaluate automated techniques. We want to be able to predict anomalies actually as they're starting to emerge. We want to detect them, diagnose them, and even mitigate them in real time. So, given a lot of accidents that you can put that up, do that in a minute, Nafi. Don't do it yet. So, given that a lot of accidents that we've actually kind of experienced with our own drones, we were really keen to see if we could have some ways to analyze them better. So our goal then is to take these techniques to deploy them on board our drones in real time so that we could have kind of analysis of critical failures as they're arising, and then also off board so that we can perform things like post-mortem analysis. So when something went wrong, can we analyze the logs and figure out what happened? And NASA is also interested in aggregating data from different UAVs into some kind of aggregated data services. And then we're also interested in benchmarks, so creating annotated data sets. So Nafi, now you can start hitting the thing again. So we support real-time analysis, real-time alerts and mitigations, and post-mortem analysis and tooling. So that's kind of where we're going to go today. Next slide, please, Nafi. So I wanted to give you a very, very big kind of high-level picture before we start jumping into the lower-level things. And I should say my background is as a software and systems engineer. So when we tend to use machine learning and deep learning and things like that, we're always kind of thinking about the big picture of how it fits in. So for our data analytics, first of all, we have data coming from many different sources. So we collect data from the environment. We collect a lot of data from the hardware, so sensors are telling us things about the position of the drones, the things that Nafi is going to talk about later about kind of vibration and compass and all those kind of things. We can collect data from human inputs as well, and just kind of like runtime things that are happening. And the yellow parts are all to do with the NASA and the FAA airspace. So this is kind of like the big picture infrastructure where our data is going to get fed. So I wanted to point out three specific things, and I numbered them 1, 2, and 3 here. The first is the runtime detection and diagnostics of anomalous flight patterns. And we want to be able to do that on board the drone. So that's basically data analytics that we have to do very quickly. Because if something goes wrong, we usually have seconds, sometimes maybe half a minute to detect it and to actually mitigate it before an accident actually occurs. The second one is the off-board analytics. So that will be more like our post-mortem analysis. Something went wrong in the flight, and this is what we use all the time. Something went wrong. We're going to run the flight logs through our analytic tools, and we're going to try and figure out what happened. And then the third one that I wanted to mention, even though we're not going to talk about it in this talk, and we've only just started doing it in our own data, but once we understand the kinds of things that lead to failures and the kinds of constraints that we want to set on our system, then we can use things like constraint managers that will basically monitor the system, check to make sure that none of our constraints are being violated, and then trigger kind of actions. In this case, it would be mitigations. So for us with the drone data, it would be something like, well, we detect through the sensors, through the time series data, that vibration is occurring. And for us, vibration is bad. It can lead to, all sorts of flight problems, oscillations, even crashes. One of the things that we can do as a mitigation is to reduce the speed or land, something like that. So that's basically the big picture. Nafi, next one, please. So I wanted to share with you an incident, and you should think of this as a kind of who done it, except it's not a who, but a kind of like what happened. So we were actually flying in a very, very controlled airspace. You can see that in the image in the top, number one. It's an airport. So we are flying our drones there. We have to go through a huge number of safety checks in order to fly there. We're doing it for an IARPA project that we're engaged in. If you click on number two. So here's our drone, and I'm not going to show all 2 minutes and 30 seconds of this, but our drone basically took off. You can see it kind of, after it takes off, it has to fly across to a position, go up to altitude, and then it has to collect visual data. So it's using its camera to collect data. We needed to do an endurance test on our drone. So we brought it back down after it finished its mission close to home, and we just hovered it for a very long time. And then long before there should have been any problem, we brought it into land. And Nafi, if you can click on number 3. And this is a replay of the final seconds of its landing. And I think you can all see that that is not meant to happen. So this was a major problem because it happened at the airport. So we analyzed the logs. Our NASA collaborators analyzed the logs. The Griffiths Air Base, New Air, which is a company that supervises all drones there, analyzed the logs. And it took a huge amount of effort. And this is the whole point in why we're trying to put analytics onto the, use analytics for the drones, because there are so many data, so many attributes, so much data to look at, so many different combinations. And you really need to have expert domain knowledge, which we've now accumulated over time, but most pilots just simply don't have it. So I'm going to leave this as a bit of a mystery until the end of the talk, because one of the, and then I'm going to ask Nafi at the end of his talk to show what happened when he ran the diagnostic test through this data and whether it diagnosed the problem correctly or not. And with that, if you go to the next slide, please, Nafi. So I'm going to hand over to the real presenters now, 2 of our team members. So Nafi is going to be talking a little bit more about the flight log data, some of the initial analysis algorithms that we used, and then he's going to hand over to Yihong, who's going to be talking about multivariate time series analysis, and then he'll hand right back to Nafi, who's going to talk about diagnostics. So after we detect an anomaly, how do we diagnose what's actually happening? And then we're going to close by showing you some of the tools that actually a third member of our team, Tony Granito, has developed to help users actually play around with the analyzed data. So I'll hand over to you, Nefi. Thank you.
Thanks, Professor Jane. Hello, I'm Nafi. I'm going to be starting with a little story of a pilot. As you can see in the screen, there's this pilot who is flying the drone, and next thing that happens, he crashes the drone. And he suddenly remembers that while the drone was flying, it was collecting lots of time series data. And he goes ahead and tries to analyze it, but he becomes confused. And next thing what usually happens is that he gets the log file posted in a forum where he asks for help. And there comes some expert person who what he does is like he takes the log, he plots the log, he detects what points were anomalous in the data. And not just that, he explains the higher level root cause of the problem, which actually happened. So the expert person, what he does is he first detects the anomalous patterns in the data, and he then explains the higher level problem, like maybe some hardware issue or motor issue. So my research mostly tries to automate the task of that Mr. Expert who does the anomaly detection and explanation. So in this talk, I'm going to focus on anomaly detection explanation. So by detection, I mean detecting the anomalous behaviors or patterns in the time series data attributes. And we refer to this as symptoms throughout this talk. And for detection, we used deep learning based methods and also basic heuristic based methods. And for explaining the higher level root cause, by that we mean that given a single symptom or combination of multiple symptoms, can we determine the higher level root cause that actually caused the anomaly? So in order to do so, we went to mine information from discussion forums and product documentations of the flight controllers to identify what are the symptoms and root causes that goes around. Then we create profiles of co-occurring symptoms and root causes to know what symptoms come with what root causes. And then we used association rule mining to learn the association between symptoms and root causes. So in this task, we had quite a few challenges. The first one is like there's huge amount of time series data that is generated by the drone. And during the flight, it's like lots of sensors. If you ever seen a drone flight log, there's many time series data, and it's very hard to determine which data actually means what if you don't have domain knowledge. And there's limited knowledge shared in the documentation, just knowledge about some basic stuffs. And another thing is like lack of annotated data. And also there's fuzzy decision boundaries sometimes between what is anomaly and what is not. And another thing is most of the knowledge on this domain is shared over the discussion forums with scattered texts. So our first approach to tackle this problem was building the deep learning based anomaly detectors. And for that, at first, we built ReSound. ReSound is a requirement process that actually looks at those information sources like domain experts, formal documentation, and discussion forums. And looking at those sources, it elicits, analyzes, and specifies the functional requirements for the deep learning based models. So ReSound basically gets the requirements for the deep learning based model. Then we use ReSound in this UAV domain to get the requirements for deep learning models for UAV anomalies. Then finally, we built some deep learning models to detect a few anomalies to validate ReSound. So these are the steps. I'm gonna briefly explain some of the steps in this talk so that you have an idea. So first thing first is we need to identify the sources of information where we can know about the anomalies. And the main sources are like the product documentation and discussion forums of two of the most popular flight controllers, ArduPilot and PX4. These are the most popular one, and most of the people we have seen, they use these flight controllers. So we look at their documentations and discussion forums to identify and the different types of faults. So from those sources, we run inductive analysis of faults, we collect the annotated data, and we create a merged list of different fault types. You can see in the table, we collected quite a few fault types, how many are like their count from different flight controllers and their description. And moving forward with that, we identified the relevant time series data attributes in the log that correspond to each of the fault types. So by this time, we actually know which data attribute in the flight log reflects which anomaly, so that we can look at that attribute and know that what anomalies we can have. And based on that, we we devised the requirements for each of the anomaly types. Say, for example, this is a requirement format for mechanical failures. Say, for example, a requirement is when actual roll pitch out deviates from the real desired roll pitch out, mechanical anomaly occurs, or when an imbalance of RPM outputs then to the motors motors occur, then there could be a mechanical failure. So we have requirements for all failures saved in this format. And after that, we use those requirements to annotate data of our own drones and train LSTM autoencoder models to detect anomalies. So what we did was we have our own bunch of drones. We get the logs out of our own drones. We annotate some logs from them. We train LSTM autoencoders to detect anomalies, and we test those autoencoders on the data downloaded from the forum. So we basically did this for 3 of the main problems that are vibration anomaly, attitude anomaly, and interference anomaly. And we had a paper on this. We report the area under the ROC curve, AUC, for each of those models. You could see here, like for 3 different ones, ViveX, ViveY, ViveZ. These are for vibration. They're pretty good. And for attitude, we had a little low for yaw, but we have the lowest AUC for magnetic interference. This image you could see. And this is because this is a multivariate problem. It needs, the anomaly is decided by correlation of multiple data streams. So that's why this was a bit hard for the model to detect. And as our goal is to run these models on drones, so we have to be very conscious about how much space or power it's taking. Say, for example, our drone runs on the Jetson Annex flight companion computer. On that computer, we don't just need to have our data analytics tool. It has our vision tool. It has our drone response of autopilot. So there's many things in there compressed. So we need to be very conscious about how much memory we are taking. That's why we are also focusing on heuristic-based anomaly detectors, which are pretty lightweight and easy to deploy. So for the top 7 symptoms, we actually built the heuristic-based detectors, and the heuristics we learned from discussion forums or documentations. So here in the table, you could see, like, for all the top 7 vibration, attitude, interference, UPS power, SC note, and EKF, we have the attributes, time series data attributes for both autopilot and their threshold values, like the anomaly conditions. For PX4, we also have the same. And we built quite a few 7 anomaly detectors to detect all of those anomalies. And these are a few detected anomalies from one of our data sets. You could see on the left, this is detection of current anomaly. On the middle, this is like motor outputs anomaly when they flip at the top and bottom values. And the right one is the high vibration anomaly. Now, my research on anomaly detection treats every attribute separately, like detecting different, like using different models for different anomalies, while Yihong's approach is more of a multivariate approach where he combines all the attributes together and detects anomalies. So Yihong is gonna say his part next.
Okay, thank you, Nafi. And this is Yihong, and I'm currently a 3rd-year PhD student. My work mainly approaches this problem from a more machine learning perspective. So Nafi has just introduced a way of more specialized anomaly detection, where he tries to look at each specific type of anomaly, such as the vibration error, mechanical error, or the compass interference error independently, and treats it as an independent problem where he solves the problem using different methods or models for each different type of anomalies. But here, my work mainly tries to develop a more general purpose machine learning model for the multivariate time series analysis. So basically, I'm just trying to formulate this drone log analysis into a machine learning problem called the multivariate time series anomaly detection. So first, we curate a new data set called the drone log anomaly, where it also collects 41 drone flight logs from the Ardu pilot forums. And instead of looking at each type of anomalies independently, we just concatenate all features together. And instead of only looking at a specific subset of the features, we look at all possible features that are important for detecting all types of anomalies. So basically, we cherry picked 15 important features in each of the flight logs. And there are 41 flight logs in this particular data set. And as we can see that we split the data set into train data set, validation data set, and test data set. And in the test data set, there are on average 15% of the time steps are actually anomalous. And our model just tries to classify each time step as anomalous or not. So we just combine all types of anomalies together. So basically this enables us to first detect all possible anomalies, and then we can plug in other models to make a more interpretable explanation on what specific type of anomalies we are encountering. But for now, with our first step is just to detect if there's any anomaly at all, like in a given time step. Next slide, please. And the model I come up with for this particular multivariate time series analysis problem is called the graphical normalizing flows. I'm just trying to skip all the technical details and introduce the model from a more higher level ideas. So basically, it leverages the idea of density estimation, where for a specific time point, it just tries to estimate the probabilistic density. And by setting different thresholds, we can say that if this particular calculated density is normal or not. So a normalizing flows is a model that which is able to estimate the density for a given probabilistic distribution. This model consists of three parts. The first one, because we are dealing with time series data, and we are interested in the temporal dependencies among those time steps. So we just encode those temporal dependencies via a transformer model. And then, since it's a multivariate time series, and there are also some interfeature correlations among different variates. So we formulate it as a Bayesian network and encode the interfeature dependencies through a GCM model because we are looking at a graph data. And then we encode the temporal and interfeature dependencies together to form a representation of all time points before the time step of interest that we are trying to detect if it's anomalous or not. And then we feed the representation into a normalizing flow model where it could calculate a density estimation, or more precisely in our task is a anomaly score. And by taking thresholds in the validation data set, we can pick a satisfactory threshold where we use these thresholds to determine if the calculated anomaly score is anomalous or not. So that's basically the model part. Next slide, please. Since the multivariate time series anomaly detection is a well-developed machine learning problem, so of course we got a bunch of baseline models to compare with, and we basically compare our model with 5 other baseline models, and we can see that it outperforms the rest of the baseline models in all metrics such as the precision, recall, and F1. We also plot the ROC curve, and we can see that our GNF, which is the graphical normalizing flows model, outperforms the baseline models in terms of the AUC score. So basically, our model also achieves a better anomaly detection performance, specifically in our drone flight log dataset. So that's basically my part, and I will hand over back to Nafi.
Thank you, Johan. So till now we were discussing about anomaly detection. Now I'm gonna discuss about our experiments on explaining the root cause of anomaly, which we call anomaly explanation. So I'm gonna remind you, like, the symptoms that we refer, they are mapped to different anomalies detected in the time series data attributes, and the root cause were the higher level problems. Maybe you could say like a hardware issue or motor issue or tuning issue. So our goal is that after the anomaly detectors detects our certain anomalies, so we can explain the root cause of the anomalies. So this is our goal for the next part. And we have an explanation tool. I am gonna explain it to you with four simple steps. These are very simplified steps. We had some steps in between, but I am trying to make it as brief as possible. So again, in order to make the explanation tool, we need the data or the information where different symptoms or root cause are correlated. So we again needed to go back our data sources. At this time, we had documentations and discussion forums, but for this project, we heavily rely on the discussion forums of RDPilot and PX4. So we downloaded all the discussions prior to 1st April 2022. We organized them by threads and posts within threads. And at the end, we had around 21,981 posts with 6.8 posts per thread. And as our goal is to map between symptoms and correlated root causes, we needed to know which symptoms comes with which root causes. So for that, first we needed to identify what are the symptoms and what are the different root causes. So in order to do so, we first identified the symptoms. From our previous work with ReSam, we identified quite a few, and we added a few with the help of documentations and again more forum reading. And we at the end identified 21 symptoms and 21 root causes. And for each symptom, we created a group by adding its variations such as tenses, numbers, persons, synonyms. And as I said already, like for each symptom, that they actually represent the anomalies found in a time series data. So for each of those symptoms, we added all the time series data attributes that reflect to that symptom. So, and made a group. So for so each symptom group, they actually have keywords that correspond to that symptom, and also the time series data attribute that reflect the symptom in the data. For example, if you could see here in the vibration symptom group, these are the keywords like vibration, vibrates, vibrating, and this is the vibe.vivex. This is a time series data attribute from RDPilot. So this is also a part of this group. This is just a small portion of this group. For each group, we have many keywords. In this image, there are some examples of different symptom groups, like here 4 symptom groups: vibration, excel, interference, attitude, GPS. And each symptom group, the orange ones are generic search terms. The green ones, they are from RDPilot, the time series data attributes, and the blue ones are PX4 time series data attributes. So this way we had 21 symptom groups, in which in total 700 keywords were found, 21 root cause group, in which we had 1236 root cause were found. In the root cause groups, we did not have any time series data attributes, but the other things are same for symptom groups. So now we have the symptom groups and root cause groups. Next task was to extract the information from the forum posts regarding which symptoms and root cause comes together. So for each of our 21,000 odd posts, what we did was we ran these symptoms and root cause keywords through the post and extracted a 42-dimensional vector, of which 21 corresponds to the 21 symptom groups, 21 corresponds to the 21 root cause groups, and each of them are binary. A 1 represents that at least one keyword from this group had a match in the post. That means, say, for example, in this slide, we had this vibration group. We run all these keywords through the posts. If any keyword matches in the posts, we have 1 in vibration, otherwise 0. This way, from each post, we got a 42-dimensional vector, which represents which symptoms and root causes were discussed in that posts. but not all, like many of the posts, they do not contain information about symptoms and root causes. So we only kept the ones that has both at least one on this side and at least one at that side, so that we can correlate or connect the symptoms to the root causes. After this process, we had 2,763 posts remaining, which contains information about symptoms and root causes. Next thing that we did was we took our data and trained an association rule mining model. So association rule mining is just relies on the market basket analysis. It gives you an idea about what are the items that comes together in a simplified way. So we got those association rules where you have a left-hand side if you have this, and it gives you confidence and lift for getting the right-hand side. Say, for example, in here, if you have symptoms, power, GPS, and attitude, you might have power issue and with a confidence and lift. And this is also an example in the table showing synapse of the rules. Like, say, for example, here, the first one is RC in out and EKF. If you have issues with this data, you might have power issue, there's a confidence and lift. So this way we got 694 rules from the association rule mining. And we ran an evaluation of this method. For evaluating, we got a test set that we downloaded the posts from the forums that were posted after 1st April and before 9th September. These were not used in the training. That's why we took everything after April. And for each thread, we ran the symptoms through our association rule mining model and got the recommended root causes by the model. And then we matched these root causes against the original root causes that were diagnosed in the forum. So basically what we do is we pass the symptoms to the ARM model, we get the root causes, and we match them against the root causes that were actually diagnosed in the forum. And based on how we generate these symptoms, we have two cases. The first case is when we use the problem description, like the initial post where the pilot posts his problem, plus the anomaly detectors on the flight log. We run the anomaly detector on the flight log to get the anomalies. So we combine these two to get our symptoms. And in the second case, we don't use the problem description. The second case is more inclined towards real-time detection when the pilot does not have time to say. So the second case, we just run the flight data through our anomaly detectors, detect the symptoms, run them through the ARM model, and get the root cause. So these two cases. So for both the cases, we plot the hit ratio graph. So what is the hit ratio graph? In the hit ratio graph, in the x-axis, you have number of recommendations. And in the y-axis, you have the fraction of threads which were diagnosed correctly within this number of recommendations. For example, here in 3, if you go here, roughly say 50%, that means in this line, with the first 3 recommendations, 50% of the threads were diagnosed correctly. So also on the left and right side, you could see like simple and iterative. These are, I didn't explain these because I don't want to go into that much complexity, but these are 2 different ways we could get the rules once a symptom is generated. So from the symptoms to the root cause, we use those rules. And these are 2 different ways we could use those rules. So for all our methods, we found pretty good results, like better than random guess. And between these 2, we found the iterative method better. And also you could see 2 lines up here. One is for primary root cause and another is for all root cause. So in some cases, there are 2 root causes. So there are multiple root causes. We determine for both primary and all root causes. Here's the overall architecture for our detection. Like the top one here is for like real-time detection, where the PX4 flight controller publishes the data. It has some, it publishes the data in a URB topics, and we have our C modules to subscribe to these topics in real time. Then we pass them to our anomaly detector through socket, and here's the ARM model that generates the root cause from those anomaly detected in real time. And below this line is for our postmortem analysis pipeline. Here, after the flight, we have the log, we parse it, we get the data. Also, there's a room for human to accept or reject any of these, and then we get the root causes. So this is the pipeline for both real-time and postmortem analysis. And here's a little synapse for our here's a real setup for our real-time anomaly detection in a gazebo simulation, where you could see like the drone is flying, and in real time, we are getting the data from EX4. We are detecting these anomalies in real time. Okay. So coming back to Jane's question, what went wrong? Here. So in that flight that Professor Jane described, we ran that through our anomaly detectors, and we found 3 anomalies: RC in out, like motor outputs, current anomaly, and attitude anomaly. And we ran these anomalies through our recommender model, and it gave us 3 outputs, like the power issue, motor issue, and GPS issue. Now, these 3, like the top 2, were actually very much matching to what Jane said. Like, we got our response from the experts who recommended us. Like, one of the experts actually said that there was a motor failsafe issue. Another expert said that there was something wrong with the powertrain. So our recommender tool was able to correctly point towards the key issues, even though it is not detailed, but it's certainly going towards the right direction. And here's our annotation tool. So these anomalies, we have our own flight log annotation and explanation tool that was developed by one of our lab mates, Tony, what Jane said about. And in here, you could actually visualize these anomalies separately with a dash box describing them. And also there is one big explanation box where you have all the anomalies, the little generated explanation like power issue, motor issue. And also at the bottom, you could be directed towards different links that could help you solving these problems. So I am going to show you a little bit more about the annotation tool which Tony developed. Let me play the video from here. So this is the annotation tool that Tony developed. Here you could add any log from RDPilot and EX4, and you could see the visualizations. I'm gonna move it a bit forward until he loads here. So he selected the log, and he selected the time series data attributes, and you could plot multiple data attributes at the same time. This works for both RDPilot and PX4. Also, there's this analyze button, after which you could actually see those anomalies in the log. So this is a pretty cool tool that Tony has developed, and this is very useful for these anomaly detection problems. Okay, I'm almost towards the end. So moving back to the problem we are facing in AnalytiXIN project. So currently we have our boxes set up in for 3 assets: EIH power, Hasmill, and the water jet. And we have the data coming from September 19th. And for all of them, currently we have the electrical properties. Like for each of them, we have 138 data attributes, all electrical, like current, voltage, true power, reactive power, etc. And we have them like sending live data to the Mega AI platform where you can visualize data like this. And moving forward, if we apply anomaly detection on them, there could be a few challenges. First of all, it's just a small data set, like it's coming for roughly 2 months now. We have minimal domain expertise. Right now, like it is all electrical data, like we have many people who knows them, but we are also in future getting the manufacturer data. For example, the water jet, I have like seen a water jet like 2 weeks ago for the first time in my life. So domain expertise could be important in here. And annotation. So in order to detect anomalies, we need to know how anomalies are reflected in the data. So annotation is an important part. To solve some of the challenges, we are now collecting baseline data. What I mean by that is we are running all the assets with different operating conditions and recording the data. For example, for the water jet, we are running it with high and low water pressure, moving the cutter in all directions, XYZ without water running, and doing this with water running. We are running this with idle versus like cutting energy consumption. So we are doing all sort of variations and recording the data to get an idea about what is normal and what is the baseline for each of these assets. And moving forward, if we build any anomaly detector models in future, then we could do like heuristic based, where we have a threshold. Say, for example, in this case, power factor, if it goes below a certain threshold, we could have anomalies. Or maybe we could do pattern recognition using deep learning autoencoders by maybe like weekly patterns or maybe weeks within the months or so. So this could be some of the future directions. And this brings me to the end of my talk, where we discussed quite a few things about our work with NASA, overall architecture of anomaly detection explanation, and finally I ended with possible approaches for AnalytiXIN project. Any questions?
Well, thank you. This was fascinating for those of us who now work with drones. Do we have any questions? Well, I have one, and please pardon my ignorance. I've never worked with drones, so I'm trying to understand something here. When you presented the drone data, you said that about 15.4% of data are anomalies. So for drone data, I mean, 15% of anomalies seems high to me, but I don't know how that works with the drone data. Is there a certain threshold of anomalies after which machines stop recognizing anomaly as an anomaly and start thinking, oh, that's normal?
Oh, that's a really good point. So the reason why there are 15 on average % of anomalies in the test set is that we cherry pick the 41 drone flight logs, which are mainly anomalous. So that's why they will experience those amount of anomalies in our test part. And the way we pick certain thresholds to determine if a calculated anomaly score should be classified as anomalies or not is through looking at the performance on the validation data set. And we pick the threshold that works best on the validation data set and then perform the evaluation on the test data set. So that's basically the way we select the thresholds for the anomaly scores.
Okay, that makes sense, because I was questioning whether that is a little too high to train the machine, but okay, thank you.
Yeah, and I think actually just kind of adding to that, you know, we had a flight, we fly drones a lot, and we had a flight that the drone flew higher than it should have flown. So we're only allowed to fly up to 400 feet. It went up to 732 feet. So we had to report it to NASA, et cetera, et cetera. So Nafi ran that one through the diagnostics. So he looked at all the flight logs and everything, and they came out perfectly. And in fact, it turned out that it wasn't an anomaly in that same sense at all. It was because we had set we had set something wrong in the fail-safe mechanism when we hit the firewall. I mean, not the geofence, sorry. And that we had a slight setting that was incorrect on the throttle. So there's absolutely nothing wrong with the drone. It flew beautifully up to 732 feet. And there was absolutely no anomalies that showed up in the when we looked at that. So that was kind of an important test for us as well, because we don't want to get false alarms. And in fact, if we move from, we can tolerate more false alarms when we do post-mortem analysis, because then the human can kind of look at it and think about it. But if we actually want to put this onto the drone in real time, we just cannot tolerate false alarms that we would then actually take actions against. And I think that would be the same as with the AnalytiXIN data.
Right. Yep, that sounds very similar, in fact. Thank you. Any other questions?
Yes. So yeah, this is Pratik Sharma from IU. I just want to say, as a software systems person and an aviation enthusiast, I really like the talk. I guess my question is for a broader audience here, that so I liked how you used crowdsourcing of domain expertise for this area, because everybody on the internet is an aviation expert, me included. But for this kind of manufacturing data, do you foresee, are there other such repositories of knowledge that we can tap into for developing this root cause analysis? Because I found that especially new and interesting. It's just a just musing for the broader group. But yeah, just wanted to say the talk was great. Thanks.
We thought about this. I'm not in, I'll just kind of say what we thought about. When we started this project with drones, we honestly had no idea, what to do with the data. So we didn't even know, what data is being collected. And so we kind of started down this road of like symptoms, and so of course we had the forums that we could go to. And then eventually we realized, well, we need to have another layer that gets from symptoms to diagnoses. So I think, in volunteering to give this talk today, we tried to say, well, here are the things that are similar, but like exactly what you're kind of, suggesting here, we don't think that you're going to find a ton of forums that are talking about the water jet and stuff. And in fact, when we wrote our paper, the ReSound paper that Nafi was talking about, we tried to generalize it at the beginning, and we tried to think of, well, you can use this method for, what can you use it for? And so we did come up with a few other domains. But I think
space observatory was one of them.
Yeah. So I think maybe the takeaway here is this is a gap for this project. We don't have these forums that can give us that starting point. But so we can take an approach like Yihong's, where you don't need to, you just kind of like are looking for anomalies in general. And I feel like that may be what people are kind of doing right now. But in the end, we need to be able to interpret it. And we need to be able to know that, when you throw all this multivariate data in and you find an anomaly, well, which bits of that are really contributing to that, to saying there's an anomaly, which are the time series and what is that anomaly, and how do different anomalies together tell us about diagnosis. So I feel like this is a gap. And we have no answer we don't think there's forums for it. I don't think any of us think that, but we think that's what we have to somehow fill the gap for this project. So maybe there's a way to get to go and elicit that, you said you're a software person like me. And, I think from a requirements engineering process, I feel like this is what we need. And I feel like we have to, the forums aren't there. We can't go and mine them. So we have to have an actual requirements elicitation process where we go and talk to the experts, stakeholders, and we go and ask them these questions in order to try and build this same kind of knowledge base for this domain.
Right. And I suspect that given the specialized nature of these machinery and their environments, curating a simple knowledge base would be very useful. And given your word, we would sort of now know what kind of questions to ask to the experts to sort of get a small but concise and useful knowledge base for these kind of problems. So I suspect that would be the way forward because of the specialized nature of this domain.
So Jane, if we have the water jet in the EIH right now, would it be helpful to just have some tests where we actually know what the faults are, and just run things normally, run things with faults, and have the operator say, this is, these are the faults that I've seen before, and reproduce them, and you actually get the data for that.
Yeah, so I think we need to go through a requirements elicitation process where we ask them those kind of questions. And then we very explicitly ask them, what, maybe they don't know about the time series data, but we have to figure out what they do know. Do they look at the data themselves, or do they not look at the data? If they look at the data, how do they analyze and diagnose the problem? So I think this is a very rigorous upfront requirements engineering process that will get us this kind of knowledge that we will then use as a kind of structure around the data analytics that we're doing.
So what's interesting is I doubt very much the manufacturing engineer would ever look at the data that we're collecting. I think what they do is they listen, they can hear things like chatter. They look at the part. They probably do a lot of analysis of the part. The part didn't do well, and so you kind of look back at, you know, what was happening, these different things. I doubt they get into the time series data, but they may look at some data from the machine or something like that. So it would be, yeah, you're exactly right. It's interesting. We should probably do a lot of analysis on how do they diagnose?
Yeah.
Right? What are they looking at, right? And if we can't measure that directly, we can measure it indirectly.
But even if they, let's say we know, you know, they tell us at this time, this machine, this went wrong. So then we need to document everything that they observed. And then we need to go and look at the logs and look for something like what Yihong did. He just ran this whole time series analysis. So, you know, did we find, you know, can we find some combination that would raise, you know, an anomaly? And in fact, I kind of think what we need is, this is, okay, I'm a software engineer, I'm not a machine learner, but I'll say what I think anyway. You know, we want to be able to detect anomalies, but we kind of want to know what's the minimal kind of combination of time series data that would be able to detect that anomaly. So if you know there's an anomaly at this point, can we kind of do some simple combinations of time series or of what things that look interesting? Because then we would be able to mimic the detection of specific anomalies, and then we would be able to feed it into a diagnostic tool. But like I said, I'm a software engineer, not a machine learner. So
thank you, Jane. Any more questions?
Yeah, I have one. So, and maybe I missed this. So I saw that in some of your time series, you have a cluster of anomalies sort of together. Is there some understanding of the correlation between these anomalies? So, for example, one can trigger future anomalies and then it self-corrects itself?
do you know which slide you were referring to?
I
just so we.
Yeah, you just passed by. Maybe going forward. Yeah, so here, for example.
Here?
Yeah, so there is an anomaly sort of together in one part of the time series, and then there is no anomaly for a while, and then it appears again. So I'm just curious, is there a...
Oh, okay. So these are heuristic-based anomaly detectors. So as the time goes by, it detects only the points at which the data crosses those thresholds. So by the time there's no anomaly, so at that time frame, the data did not cross the thresholds. So that is why detecting anomaly at one point, after some time, the anomaly is not there. So for example, this one is a vibration graph. At these points, the model detected higher vibration. So if these time parts were flagged as red, so detecting anomaly. Here, vibration lowered, it did not detect, and here vibration again rose up, it detected. So you could see some of the points were not detected because we ran a moving average value here. So it detects, but it takes into 10 points at least, so that like the average of 10 points, if it goes beyond 30, then it detects anomaly. So in these points, even though there's certain clicks, but the points nearby, they are low. So that's why there is no anomaly. So again, running in here, you could see like all the points, they have very low vibration, not anomalous. Then coming back here, it found 1, 2, 3 points again. So that is why in between some points, there's no anomaly, but there's anomaly here and there.
And it could have correlated with something else like thrust, or
yes,
for example, some kind of yaw or something that was something else that was going on.
Yes. So at this point, like what Jane said, like at this point, maybe the thrust was high so that the drone was pushing hard to go up or straight. The vibrations rose up. Here it was pretty stable because thrust was low. That could be it.
And I think another thing that's interesting here, because Nafi is saying, we deliberately develop these heuristic ones which are simple versus some of the kind of the deep learner ones which are better probably, but the heuristic ones for running on board are much faster. So we kind of think that it might be good to have a hierarchical. If you want to be able to detect things in real time, it's got to be fast, at least for us. And I don't know what the patterns would be on the machines, but for us, usually when something goes wrong, you might have, if you're really, really lucky, you have 2 minutes as it starts to build up, but often less. So we have to respond really quickly.
All right, thank you.
Any other questions? Well, if there are no more questions, Professor Cleland-Huang and your team, thank you very much for this actually fascinating seminar. I've now worked with drone data and it looks very cool. So thank you very much. And then we'll see everyone for the next seminar that will be held by Indiana University. Thank you very much.
Thanks, everyone.